In this video, we're going to wrap up the introduction to proofs with mathematical induction. So, we have already discussed the following: direct proof, contraposition, and vacuous trivial. So, proof by contradiction, equivalence, and this is the last one, mathematical induction. So to begin with, we're going to come up with a visualization for induction, and the most commonly used is the domino effect, because the idea of induction is first the domino should fall. So the first domino should fall. So we could formalize this as the base case or the p sub 1, or sometimes that is p sub 0 depending on the sequence. Next, for the domino to continue falling, then I could choose an arbitrary domino, say p sub k, and given that pk is there, it should follow that it has a next element for the continuous falling, so pk plus 1. And that's basically the essence of induction. This will be called as the base case, the first fall, and this will be the inductive case or an inductive step. Okay, another visualization will be a ladder. So proof by mathematical induction, you have if there is a first step, so P1, then we can choose an arbitrary step in the ladder, P sub k. This could be any step, could be in the middle or in the last one, and that should imply a next step, so pk plus 1. And again, the p sub 1, this will be the base case, and this inductive step can be proven now by direct proof. That is the inductive step. That is, you're going to assume that an arbitrary k exists, so p sub k exists, so this is true, and somehow you should show that there's a next step existing for the inductive step to be satisfied. So formally, proof by induction is following the induction principle, where for any statement involving a positive integer n, the following are true. First, the statement holds for n equals 1, or that is the base case. And secondly, whenever the statement holds for n equals k, so property pk, implying it must be also true for the next element. Then the statement holds for all n. So that is the generalization based on these two properties. Again, this will not be a proof by induction if it does not contain any of this. So it should have the base case and the inductive case, or the inductive step. So let's come up with an example. For example, prove the following. So 1 plus the sum of natural numbers is equals to the arithmetic series n over 2 and multiplied by n plus 1. So again, it involves two steps. First will be the base case, and secondly the inductive case. So for the base case, I will simply show that P of 1 is true. Again, the verb here is show, so therefore you're going to get the left hand side and somewhat equate it to the right hand side. So I have the left hand side, so I have a 1 element, and is it equals to, when I substitute 1, say 1/2, and then 1 plus 1, and that is now 2 times 1/2. Therefore I have shown 1 is equals to 1. So the left hand side is equals to the right hand side. So base case is satisfied. So the first push of the first domino has been satisfied. Next, for the inductive step. Inductive step again will involve two scenario. So let's try to rewrite this one. So firstly, I'm going to assume that this is true, or assume P sub k, an arbitrary number k, is true. Then after that, you're going to show that pk, the next element, plus 1 is equals to, or is also true. And again, we have to show this. It's not an assumption. Okay. So we are going to assume that, let's use another color for this. Say 1 plus 2 plus 3 and so on up to k is equals, again, k could be is an arbitrary number, so is equals to k over 2 k plus 1. So again, we don't need to prove this. We simply assume that this will be true. What we are going to show is the next element. So we're going to show that 1 plus 2 plus 3 up to k plus 1 also follows the formula, which is the highest element, k plus 1 over 2, and then k plus 1 plus 1. Okay, and the usual pattern in induction is the substitution. Say this one, pk will be basically substituted to the next step, the showing part. So this will be substituted, or to be specific about it, this one will be substituted here. So this is the usual pattern in an induction. Now, after substituting, it's simplification. So substitute first, then we have a k over 2, k plus 1, and plus k plus 1. So is equals to, let's just represent this as the right hand side. Now it will be algebraic simplification, so let's manipulate the left hand side. So left hand side is equals to what I do basically is simply factor out the k plus 1. So if we factor out k plus 1, I'm referring to this, k plus 1, then we will have k over 2 plus 1. And if you're going to remove the 1/2 here and put it outside, so we will have a k plus 1 over 2, and this will be k plus 2. So this will be the right hand side, and basically they are equal. So the right hand side is k plus 1 over 2, so k plus 1 plus k plus 1 plus 1, or that is basically k over k plus 1 over 2, k plus 2. Therefore, we have shown that when we assume that pk is true, then it follows that pk plus 1 is true. Therefore, with the principle of induction, if you recall, the statement base case holds true, and it follows that whenever the statement p k plus 1 is also true, then the second case has been satisfied. Of course, the base case was satisfied early on, as p sub 1 is also true. Given these two conditions, then the statement holds for all positive numbers or positive integers, and that's it. So to end off, we're going to have an exercise which you're going to answer. So prove that the sum of the first n powers of 2 can be computed by 2 to the n minus 1. So the first step in solving this, although I will solve this next video, is to understand what is really the left hand side that will basically match the right hand side. So sometimes the confusion is in the left hand side. That's it.